This is an old test question, but it's also a good illustration of how computer memories work. This circuit diagram shows one way to build a 2-bit memory out of muxes and D flip-flops and some other bits and pieces that we haven't filled in yet. We're going to discover what goes here and here in the course of the question. But let's look at what we have got for the moment. At the heart of the circuit are 2 D flip-flops. They're both connected to the system clock, and each of them is controlled by a mux. Also, their outputs feed into a mux. What's controlling the output mux? Well, this signal A, which stands for address. An address is a pointer to one component of a memory that we wish to access, either by reading or by writing. And we can see that this address line controlling the mux selects whether to read Q0 if A is 0 or Q1 if A is 1. The selected signal will end up going to the data output. However, the memory is not just read-only. The memory can also be written, and the read-write functionality is controlled by this line, the C signal, C for control. If C is 0, we're supposed to be just reading the memory, whichever bit is selected by the address line. If C is 1, we're supposed to update one of the 2 bits of the memory, taking the value from the DIN, data input line. If C is 1, the address signal tells us which of these 2 to update. Now we can see the 2 flip-flops are each controlled by a mux, and the mux is selecting between 2 possibilities. The one possibility, if the mux gets a 0 signal, is that we will send the data input through to the flip-flop. And the other possibility, if the mux gets a 1 on its control line, is that we will send the old value of the memory cell back to the flip-flop. So that's to say, in each of these 2 locations, the mux is selecting between updating the D flip-flop from the data input or retaining the old value that was already stored there. So that's exactly the behavior we need if we want either to preserve the old memory or overwrite the old memory with a signal from the data input. So we're now asked to explain what the behavior of this circuit ought to be. And we do that by writing a characteristic table. As ever, we tabulate the possible binary values of the inputs. So the address is either 0 or 1. The control signal either says 0 for read or 1 for write. 0 for read, 1 for write, and then the data input is 0 or 1, 0 or 1, 0 or 1, 0 or 1. And now we're asked to give the signals which are controlled from these 3, namely the next state of each memory bit and the current output. And we are allowed to express these signals in terms of their previous values. That's to say, in terms of Q0 of t and Q1 of t. So let's first of all go to the data output. We can see that's directly controlled by the mux. And the mux is taking its cue from the A signal. So we can see that the data output is going to be Q0 of t if A is 0. And it will be Q1 of t if A is 1. Now, let's look at what happens to bit number 0. in the memory. If we're addressing the bit, but we're reading, then the memory at the next time should still be the same as the memory is now. So we should stick Q of 0 of t in here. But if the control signal says 1 and we are addressing bit 0, then the memory should be updated with whatever's coming in from the data input. Meanwhile, if we're addressing the other bit entirely, then certainly bit 0 should stay the same. Moving on to bit 1, again, if the address line says we're paying attention to bit 0, then bit 1 should not change. It should carry on remembering whatever it was remembering before. Now what happens if we are addressing bit 1? Well, if we're reading bit 1, then bit 1 should not change. But if we're writing to bit 1, then bit 1 should become a copy of the signal coming in on the data input. So this is the behavior that we want this memory circuit to have. Now we have to figure out how to get it. We have to build these two components, which have been named arbitrarily foo and phi, and we've got to control the D flip-flops appropriately. We're asked, just as a reminder, to say what a D flip-flop does by giving its characteristic table. So again, we tabulate all possible control signals, and then we have to say what the next state is in terms of the previous state given the control signals. And in the case of a D flip-flop, the previous state isn't actually relevant. The next state will be taken directly from the D input. Q of t plus 1 equals D of t. So that tells us that the signals we should send into the D flip-flop are exactly the signals, the value that we want to store. So that is going to help us enormously figure out how to control the mux, because we're choosing between one signal we could store or the signal that's already stored. So now let's figure out the truth table for foo. This is foo. Income A and C. And we have 0 or 1, 0, 1, 0, 1. And let's figure out what foo needs to do. The characteristic table will help us. We're looking at each of these pairs of lines. We need Q0 of t plus 1. Foo is basically controlling D0 of t, and thus Q0 of t plus 1. So what happens? We can see that when we have A and C both being 0, we want Q0 of t. And that's the third input to the mux. That's the signal we'll get if the mux controller says 1. So the mux controller had better give us a 1. That will give us Q0 of t in this case. If we're addressing 0, but we're writing, then we're looking here. We want to get a copy of dn of t, and that's the signal we'll get if the mux control line has a 0. If we're supposed to be addressing the other bit entirely, then again we're going to want q0 of t, so the mux had better get a 1. What then should the foo circuit do? It should take these inputs and give these outputs. And we've been asked to build this circuit with NAND gates, which is rather helpful because we want, we've got 3 1s and a 0 in the truth table. So what do we need to do? We need to make sure that we're not on this line. And that means we need to make sure that A is 0. We're detecting if A is 0 and C is 1, and then negating that situation. So we figured out what foo is. It's now, how about phi? Updating my picture. We want to work with the Q1s. Q1 of t plus 1 here. If we want to address bit 0, then whether we're reading or writing, bit 1 is going to stay the same. We want to select Q1 of t here, and that means what do we need to send to the mux? We need to send a 1 to the mux. If we're addressing bit 1, but we're only reading, then again, we need to make sure that Q1 stays the same. So again, we need to send a 1 to the mux. It's only in the situation where we're sending 1 on the control line, meaning write, and we're 1 on the address line, meaning we're addressing bit 1, and 1 on the control line, meaning write, that we need to pay attention to the data input and send a 0 to the mux. Now, can we build something with this truth table from NAND gates? Well, yes, very easily, because this is exactly the truth table for a NAND gate. So phi is just NAND itself. Now we've filled in the control circuitry for the muxes that make sure each memory location gets updated either with the data input or with its old value according to the address and control signals. We've built a 2-bit memory.